So we are picking up where we got to last time. This problem number 4 is from our previous example sheet, and we did not get to it on Tuesday. So let's take a look here. The problem tells us about a long jumper who's trying to improve his distance through some kind of conditioning routine. And it's believed that using this routine will result in him being able to jump further. Before doing this conditioning routine, the jumper was averaging 24.5 feet. Now, since this is before anything happened, that would be the value that we consider the status quo, right? That's what has previously been established. But now the jumper goes through a routine, series of conditioning routines. At the end of this, does 30 jumps over the course of a week and has a new average of 25.2 feet with a standard deviation of 1.26 feet. And we want to establish here whether the new sample gives any evidence that he has actually increased his average jumping distance. And again, increased directional words tend to be important here. And you can see here we get asked to do a hypothesis test and do it at a 3% level of significance. Remember, that is also an evidence level. And for a comparison, you can think of that as in a criminal trial, wanting to prove something beyond all reasonable doubt. So the evidence level you can think of as how much evidence is there for the null hypothesis. And if we say 3% level, that means if there's less than 3% evidence for the null hypothesis, we're going to reject it. If there's more than 3% evidence for the null hypothesis, we're not going to reject it. So we want to test here your null hypothesis that's always formulated in terms of the status quo, right? That which had previously been established. In this case, 24.5 feet. And the alternative, this is where this directional word is so important. If we say there's been an increase, that means the new average will be bigger than 24.5. Now, what does our sample data say in this case? The 30 jumps represent our sample, and those have an average of 25.2 feet, and the sample has a standard deviation S of 1.26 feet. So what test would we use here? Well, the population standard deviation sigma is unknown. And so a t-test is better to use than a z-test. Always check for that. If we're doing a z-test, we're doing a t-test, and that'll be y bar minus mu naught over standard error. The only difference if you were doing a z-test is it would be y bar minus mu naught over standard deviation. And standard error and standard deviation are calculated in the same way. In one case, you just use sigma over square root of n. And in our case, where we don't have sigma, the standard error is given by s over square root of n. So in this case, 1.26 over square root of the sample size of 30. And so our standard error here is 0.23. So this lets us now calculate the t-value. The new sample average is 25.2. The value under the null hypothesis is 24.5. Our standard error is 0.23. And so we therefore find a t-value of 3.04. Now, what do we do with it at this point? Once you've calculated the t or the z-test, you visualize a bell curve. If you were using a z-test, it would be a normal bell curve, but since we're doing a t-test, it would be a t-bell curve with n-1 degrees of freedom. So in this case, it would be a t-curve with 29 degrees of freedom, always 1 minus the sample size. And we observe a value of 3.04. And our alternative says greater than, which means we want to look at the part of the bell curve that is greater than 3.04 or above 3.04. So that shaded part, that represents our p-value. Now, we can now use the t calculator. And in the problem set from Tuesday, I specifically had the link to that. But if you just go to Google and you punch in t calculator, then at least on my algorithm, the first link I get is from a page called StatTrek, which you should see on your screen right now. And so there you just go and you enter the degrees of freedom, 29, the t-score that you calculated. In our case here, the t-score is 3.04, and you hit calculate and it gives you a probability. Now, the probability here is always the part of the bell curve to the left of the t-score. So we have that 0.9975, but visually what that does is to the left here, that part is 0.9975. So if we want to know how much is in the tail, we have to subtract that from 1, which in this case gives us 0.0025. Or if you multiply that by 100, you get a percentage, which in this case still is 0.25%. So here our p-value is 0.25%. Our evidence level is 3%. So have we met the evidence level? No, we have not. So we reject the null hypothesis. 3% represents how much evidence we need to see to not reject the null hypothesis. So small p-value, small chance that the null hypothesis is true, and so therefore we reject it. Now, in this case, this is probably a good thing. Right, our null hypothesis said that the athlete is still jumping 24.5 feet on average. The alternative says there's been an improvement. And if we reject the null hypothesis, then the most plausible truth is what we state under the alternative. So we would say here that the sample evidence suggests that the conditioning has worked. And what's happened as a result is the athlete now jumps further than what the null hypothesis value had been. And it's important to make sure that you clearly formulate a conclusion. On any hypothesis testing problem, about a third of the points for that problem will be given just for how you write down your interpretation. So this is the part of statistics where it's not just about doing the calculation, it's about how you then interpret your findings at the end of the day. That will always be very important here. Any questions about this example? Let's move on to our next one, problem number 5. Now, what we're getting into with problems number 5 and 6 is looking at the similarities and the differences between using confidence intervals and using hypothesis testing, because they're two different approaches to trying and answering the same types of questions. And specifically, the video lecture from yesterday got a little bit into that. So it talked about how a confidence interval is a data-centric method and a hypothesis test is a model-centric method, but very often they still give you the same result. So we're going to look at an example dealing with a proportion and then another example dealing with an average. In this first example, a garden center has leftover vegetable seeds. They want to store them for the next spring, but they don't know if the seeds will germinate at the same rate a year later. But the manager then luckily finds a packet from the previous year, so takes the green bean seeds from a year ago, plants them at it as a test, and notes that the packet claims a germination rate of 90%. So part A says, in the sample, 171 of the 200 seeds sprout. And based on that, we want to calculate a 95% confidence interval for the true germination rate. And the rest there just says, we can assume that the packet represents a random sample, that independence holds. You know, you should make sure that you know all the assumptions for the different tests, but here we're not going to check them. We assume that they are valid. So if we're doing a confidence interval for a proportion, the formula is p hat plus or minus z star times standard error, where if you're dealing with a proportion, the standard error is given by square root of p hat q hat over n. So in this case, what is our p hat? What is the sample germination rate? Well, that would be the 171 over 200, which in this case corresponds to an 85.5% germination rate. And then our standard error is given by 0.855 times 0.145 over 200, square root of that, and that gives us 0.025 or a 2.5% germination rate. And finally, we need to find our Z star value. Now, Z star for a 95% confidence interval corresponds to the value 1.96. And this is where I said you can cheat the system a little bit. You can actually use your t-table, which is used for confidence intervals. But on the t-table, just scroll all the way down to where you have an infinity, because on the t-table, the infinity corresponds to a normal distribution. And so if we want a 95% confidence interval, that tells us in the middle of the bell curve, we want 95%. So what's left in the two tails? 5% or 0.05. So in the table, you find the two-tailed value, 0.05, and you just follow that all the way down to the part of the table that corresponds to the normal distribution. In fact, you could have gone from the bottom up, because here it gives you the confidence level and it says 95%. So that's where the Z star value comes from. Now we can plug in all our values So I'm using the confidence interval formula, 85.5% plus or minus 1.96 times 2.5%. And we can always just write the lower and upper value in parentheses as a summary. This ranges from 80.6% to 90.4%. And so the question concludes with asking, is this confidence interval consistent with the claimed germination rate? And the answer would be yes. The confidence interval contains 90% as a possible germination rate. And so the confidence interval is supportive of the true rate being 90%. Like the confidence interval says that's a possibility, because according to the confidence interval, the true rate based on the data we've collected can be anywhere from 80.6% to 90.4%. So at the 95% confidence level, we cannot exclude 90% as a possibility. Now, what would this problem look like as a testing problem? Say we wanted to test the null hypothesis that p is equal to 0.9 against a general or a two-sided alternative. So that means our null hypothesis says the true proportion is 0.9, and our alternative says it's not equal to 0.9. That's what general alternative or two-sided alternative means. There's no specific direction. This 0.9 value, this now represents our P0, the value under the null hypothesis. And for a proportion, if we're doing a test, we use a Z statistic, and it's given by P hat minus P naught divided by SE naught. So we have P hat, we have P naught, we need to calculate SE naught, and that's this standard error formula, but with P naught and Q naught instead of P hat and Q hat. So in this case, 0.9 times 0.1 divided by a sample size of 200 will give us a standard error of 0.021 or 2.1%. Note here that we had a 2.5% standard error under A, and we have a 2.1% error here. That's the difference, especially with proportions. That's where things can deviate, because under the two approaches, we can have different standard errors, and different standard errors can result in different conclusions. But let's follow through on this one. So our Z-test, it'll be our estimate of 85.5% minus our null value of 90% divided by our standard error of 2.1%, which gives us a Z value of negative 2.14. So how do we translate this into a p-value? Visualize your bell curve, Z-test, so it's a normal curve, centered at 0. We have a negative 2.14, but because the alternative is two-sided or non-directional, it actually means that we need to find two sides to our bell curve. We need to take both the negative and the positive value. So we need to find how much of the bell curve is in both tails. Now, here again, we need to turn to our normal table, and we need to go look up in our normal table negative 2.14. So negative 2.1 and the extra 0.04 that corresponds to 0.016. Remember, the standard normal table represents area to the left. So that's telling us the area to the left of negative 2.14 is 1.6%. But by symmetry, the area to the right is also 1.6%. And that means, in this case, our p-value is 3.2%. It's just 1.6 plus 1.6. We are comparing that against a 5% significance level. And so the p-value is small, which means we reject the null hypothesis. Our null hypothesis said the true germination rate is 90%. But our sample data now says 90% is rejected. Based on the data we've collected, 90% is not a plausible value. It's a different number. So note, I specifically put in this example because using the confidence interval, we conclude that 90% is a plausible value. Doing the hypothesis test, we find that 90% is not a plausible value. And the whole difference here can be explained by the two different standard errors under the two approaches. It doesn't frequently happen that the two methods will give divergent conclusions, but it happens here, and it has everything to do with the standard error. So know that you can get discrepancies like this, and unfortunately, there's no way to say which one is the correct conclusion or not. It kind of depends on whether the person doing the analysis prefers a data-centric approach or a model-centric approach, because they start from inherently different places in how the calculations are done. So that was an example dealing with a proportion, and problem 6 is something similar, dealing with an average. Now, the good news is with the average, the standard error calculation is the same under both approaches. And so if the standard error is the same, you're not going to have these divergent conclusions. So at least as far as an average goes, you should have consistency between confidence interval interpretation and doing an equivalent hypothesis test. So here, a researcher is studying cholesterol levels of American adults who eat frozen pizza. Takes a random sample of 25 people in Fort Worth who eat frozen pizza once a week, and in the sample finds that the mean cholesterol level is 233.5 with a standard deviation of 13.8. So for our sample, the average is 233.5, standard deviation is 13.8, and we took a sample of 25 people. Again, because we're using S, we need to use T for any of our calculations. So part A asks us to calculate a 99% confidence interval for the mean cholesterol level. So the formula for the confidence interval here is given by y bar plus or minus t star subscript n minus 1 times standard error. Standard error here is calculated as S over square root of n. So 13.8 divided by square root of 25 gives us a standard error of 2.76. Next thing we need is our T star value. Now, we're doing 99% confidence. What that means is if you're visualizing a bell curve, that in the middle, you want 99%. So the two-tailed value is 1% or 0.01. That's how much is left in the two tails. And remember, degrees of freedom will be sample size minus 1. So we need to go to our t-table, use 24 degrees of freedom, and either look up a two-tailed value of 0.01 or a 99% confidence level. So going to my t-table, 24 degrees of freedom, 99% confidence, which corresponds to two-tailed of 0.01. But that means I'm looking in the row 24 in the 99% column, and that gives me a t-star value of 2.797. So now we can plug in everything into our confidence interval formula. So it's 233.5, that's my y-bar value, plus or minus my t-star value times my standard error. And this gives me a confidence interval ranging from 225.78 to 241.22. The question concludes by saying, if a healthy cholesterol level is 220 or lower, does the confidence interval support that this population has a healthy level of cholesterol? And the answer is no, because 220 is outside the interval. In fact, the lowest possible value that the interval allows for is above the healthy range. So you can say the confidence interval lower bound exceeds a healthy cholesterol level. And so it's not plausible that this specific population has a healthy level of cholesterol based on the confidence interval that we've constructed. So the confidence or the cholesterol level here is unlikely to be healthy at the 99% confidence level. You should have a habit of stating what your confidence level is or what your evidence level is, etc. Now, part B has us test the null hypothesis against two-sided alternatives. So we're trying to solve the same problem, but we're now taking a model-centric view. And the alternative here is said to be generic or two-sided. So it just means mu is not equal to 220. So the value under the null hypothesis, that's what we call mu naught. And here, so we're using a t-test, y bar minus mu naught over standard error. And y bar was 233.5 minus mu naught is 220, divide by that standard error we calculated earlier, 2.76, and this gives us negative 4.89. So again, visualize your bell curve, centered at 0, you have negative 4.89, and because it's a two-sided alternative, you go and include the positive value as well. So the p-value here corresponds to how much of this t-distribution with 24 degrees of freedom corresponds to the shaded region of the bell curve. So you can go and use that TCDF calculator on the StatTrak website, you'll put in your t-score is negative 4.89. You'll put in degrees of freedom is 24, and it will tell you probability that t is less than or equal to negative 4.89 it'll give you a 0. So what this is telling you is that there's 0% effectively in this tail, which means 0% effectively in the other tail. And so our p-value here is 0%. We're working with a 1% evidence level. P-value is less than the evidence level or the level of significance. And so we reject the null hypothesis, which means we conclude cholesterol level is not 220 on average. That was our null hypothesis. So we are concluding that it's some different number, which means that this population, again, does not correspond to one having a healthy average cholesterol level. So in this case, confidence interval and hypothesis testing give us consistent results. So I'll take some questions in a minute, but what I really quickly want to run through here is just what you should be focusing on for test 3. Now, primarily, this will correspond to the contents of chapters 14 and 15. What should you be prepared for? You should be able to, for a sample proportion and also for a sample mean, you should be able to do a confidence interval. Now, here's the little bit of extra work you'll have to do to prep, because the proportion confidence interval is in chapter 13. So you don't have to study all of chapter 13. It's just this formula, p hat plus or minus z star times standard error. But that will come up in the test, and it's important to the rest of the work in chapters 14 and 15. So you need to be able to do confidence intervals, and you also need to be able to do hypothesis testing. And especially when it comes to a mean, t versus z, and for a proportion, it will always be z. And for both the confidence interval and the hypothesis test, you need to be able to know what the assumptions are that go into those. And the test will be available on Monday, and it will be up all day Tuesday. I'm trying to remember exactly when I said it runs through, but I passed that information on to you, and I will make sure to remind you of that tomorrow. So tomorrow I will also post a set of review problems, check later in the day tomorrow. Those will be important for preparing for the test. And the test will work in exactly the same way. You will have 2 hours from when you start until you have the test uploaded. So please use the weekend to prepare for that.